My facial, I was gonna say my eyebrows have grown back, but I realized I can't work my video. I was gonna turn my video on, but there's a problem with it. But okay, whatever. So last day of class, and um, so I guess we should talk about the final exam. The final exam is going to be just like the first one, distributed over like I think a 36-hour period in which you can take the 2-hour exams. I should say that, yeah. The exam is only 2 hours. So it's going to be a lot shorter than the exams you'll see online right now. And we're doing that just to like reduce how much stress you might have to deal with at home. That's something that the higher ups above me decided. And then, okay, so the exam is in 2 weeks. For office hours are the same, excluding the Friday, I guess the Friday from today. So excluding that, I think that's May 1st, excluding Friday. Because that's the day you'll have the test, and probably I'll figure out a time to have my cell phone number available and open to you for a 2-hour period. So that'll be the same thing. If I've forgotten anything, I will just make an announcement. You can expect me to write an announcement by now because I am really into those. And then the last thing I really wanted to say is that I don't know how much at Rice they pushed you to do the teacher evaluating instructions, teacher evaluations, I mean. At my university, it was like required. You actually had to take 20 minutes out of your class to do it. So I don't know if they need you to do it, but if it's an option, really do consider giving me any sort of positive or negative feedback that you have to say. Especially, I mean, not to the job market is going to be quite competitive in a little bit, and to get teaching jobs is going to be pretty difficult. And they take what you have to say to heart pretty well. And if you're required to do them, okay. So okay, never mind. Just be honest then. Everybody, be honest in your truth, in your truth with your teacher evaluations. I think we all had I hope we all had a very positive experience together this semester. Or at least I had with every single one of you. So I hope it was the same way. Okay, so let's just do some math. Let's get to math. So, again, no new topics. The last topic that we learned that was new was Divergence Theorem on Monday. And so I think today is just going to be different applications of Divergence Theorem and Stokes Theorem. So let's do an example. Okay, so I don't want, should I say this as a claim? I'll say this as a claim. Yeah, claim. Yeah, I like doing this so you can see how proofs are going to be written if you take proof classes. So claim is that y over any oriented surface S, no, I shouldn't say y. A claim should be a statement. That was confusing. So the claim is that over any oriented surface S with normal vector n and whose boundary is C, the unit hemisphere, not hemisphere, the unit equator in 3 space, in 3D, oriented counterclockwise when viewed from above. Okay, so tons of words right here, but you should just think in your head, all we have is an S, a C, and an N. So all we have right now is shapes, but the boundary of the shape is definitely on that horizontal circle on that is in Z equals 0. Okay, so I haven't said anything else, so now we'll say let B be a vector field defined on S. Then this is the double integral of the flux. What am I going to do? 0, 0, 1, n dA over S is equal to 2 pi. So I'll tell you how I came up with this. I'm going to copy this and bring it to the next side. But I thought about this when I wanted to discuss. Oh no. There you go. When I was first planning on giving, sorry. Oh my gosh, I'm trying to do two things at once. Go over here. Nope. Oh my gosh, it's a mess. Okay, copy this. Struggle bus today. Copy. Move it over, and we paste. Okay. I was thinking about fun, different kinds of flux examples to do all together. So I thought, I literally thought to myself, well, let me make them do the double integral over like a cone. So that's a cone with a boundary at that unit circle C of 0, 0, 1, N, dA versus I was going to have you all do the double integral over the hemisphere with the same boundary as the cone. I was going to have you compare which one was bigger, and I guessed that this one was going to be bigger. I had somehow convinced myself of that. But I actually rolled up my sleeves of the computation and found out they were both 2 pi. And then I kind of realized the way I did it was Stokes theorem or divergence theorem. So the idea is that any surface, so any single, here's C on the bottom, and here's any sort of crazy wonky surface S with outward pointing unit normal. So this one, that's N. And V is that constant vertical vector field. I'm not even going to draw it. But if you want to take the flux of that vertical flow through the net, it's always going to be 2 pi. So that's the claim. This is I'll highlight the statement we are trying to prove. Okay, so to start proving this, I actually have 2 proofs. So proof 1. This is going to use divergence theorem. So what we have right now is in my upper right-hand corner, I have this 3D surface, okay, and it's hovering over my boundary C in the XY plane. So remember, the C is unit circle. Okay, the divergence theorem, we have an S, but our S isn't closed. S is not closed, so in order to use divergence theorem, we will seal the boundary. So seal S with S twiddle. So S twiddle is going to be the flat disk on the bottom. So I'm going to zoom in to the top corner. I'm going to draw you in. Let's do it in peach. Okay. This is S twiddle, and I'm going to just tell you which normal vector field it's going to be. It's going to have out this downward pointing N. So we seal S with S twiddle and give orientation of S twiddle, okay, to be the downward. Okay, so now the reason why I've chosen the downward normal is because if I use that agrees with the outward orientation from the inside of omega. So I haven't even told you what omega is. Omega is the solid on the inside. Omega is the 3D region. So divergence theorem says that the triple integral of the divergence of what's my vector field, I'll highlight it over here. A vector field is that thing. It's a constant vector field. So 0, 0, 1 over omega, that's the 3D region inside the net, is the sum of the 2 double integrals. So I've got S and plus S twiddle and 0, 0, 1, N. Oh gosh, I've run out of space. So I should never do it this way. Okay, dA, and then 0, 0, 1 dot N D A. Okay, so that's what we've got over here. I can actually move to this next page. I'm just going to copy and paste because we have like basically one of the integrals that you're seeing in that equation is the one we're trying to understand. I'll use my highlighter. I love this highlighter. So up at the top right here, that's the integral we're trying to understand the value of. We're trying to show that that thing is 2 pi. And now at the bottom, I see 3 integrals, and the one spot where I see that appear is, that's this thing, the integral over s. The idea is that the thing on the left and the thing on the right are super easy to compute. So let's go ahead. Let's go to the other, this is page 2, and I'm going to copy this. Copy. Okay. Paste. All right. So let's figure out what these two sides are. So the left, I'll highlight in yellow. This will be blue. But yellow is easily seen to be 0 because why? If you look at the divergence of a constant vector field, that's the derivative of something constant, so that's 0. So divergence of a constant vector field is 0. So yellow, or left-hand side, is equal to 0. Okay, easy. That was an easy one. That was freebie. This one over here isn't too bad. Okay, so let's actually go ahead and compute what this thing is. Here, in this blue picture, what was the normal? Did I call it n or n twiddle? I just called it n. So remember, in this case, n is also constant. It's 0, 0, negative 1. Because I wanted that downward, so I could be pointing outward. It's kind of the logic there. But that dot product is pretty easy to compute. So that means this blue piece is a double integral over s twiddle of 0 times 0 plus 0 times 0 plus negative 1, I guess positive 1 times negative 1. Okay, and that's dA. Okay, and if you figure this is just negative 1, and so this thing is negative double integral over s twiddle dA. And then you see that whenever you have this piece right here, that's just the area. That's just the area of the whatever region it is. And this is the easier one. This is the thing we know the area of. This is the area of the unit disk. And so that's just area of a circle, which is pi r squared, and our r is 1. So this is, did I lose a 2? No. Where's my 2? I did something wrong. I did something wrong. No. No, this is right. Okay. This is actually correct. Okay, I typed this wrong. It's not 2 pi, it's just pi. This is correct. Okay. Okay. So that's the thing we're trying to show. Sorry about that. It's a single pi, and over here we see the reason why it's a single pi is because now that I see yellow is 0, baby blue is negative pi, then I can rearrange the whole equation and I get pi equals double integral over s 0, 0, 1 dot n dA. The only reason why I got confused with the 0, why I had a 2 pi, is because on the first example that I did on my own last night, I had, for a reason, I had a 2 here instead of a 1, but that really didn't make any difference. Okay, so that's kind of a powerful thing. Like, no matter what the surface is, however that S is bending and wiggling around up top, hovering over the green C on bottom, it's going to have the same flux. And you can prove that by divergence theorem. And it's funny because I was going to have you all on homework individually compute this and individually compute this, and then find which one's bigger, and then maybe provide some sort of geometric explanation, like, oh, well, most of the time the sphere has vectors that are closer to straight up, so most of the time the dot product is big, or something like this. But I was really surprised to learn that both fluxes were equal to the same number, no matter what. Like this cone, this hemisphere, or this like jellyfish net. And jellyfish net is in SpongeBob SquarePants. That's right. Okay. Okay. So that was proof 1. This proves that no matter what your S is, your answer is going to be pi. Now, there's a second proof that uses Stokes theorem. So I really like this because we can see the same thing using 2 different arguments, one using Stokes, one using divergence theorem. So let's use proof number 2, that the double integral over S 0, 0, 1 dot n dA is pi. And this uses Stokes theorem instead. Okay. Okay, so the key thing to note and be keen of is the following. So I will like on my own, sort of unprompted by the question, unprompted by any other impetus, something I just kind of thought about on my own, I will define and pull this thing out of a hat. I will define v of x, y, z to equal, okay, I gotta be careful. So I want, I think, negative y over 2, comma x over 2, comma 0. Okay, so this is the more difficult proof, but I think the more satisfying proof, because it kind of requires you to pull something out of thin air. You in reality, when you do math and you try to find, and this does happen in the wild, it's typically something you've reverse engineered. So typically you wouldn't just guess this on the first try, you would reverse engineer it. But the reason why this is interesting is you can actually compute curl of v is going to be equal to 0, 0, 1. And so now this, I'll use my highlighter in green, this beloved quantity that we're trying to prove is pi, I'll write this out for you. I'll copy the green up top. All I'm going to do in this next line is replace what we know an alternative way, a more complicated way to describe the vector 0, 0, 1. This is merely the double integral over s of curl of v dot n dA. So that's pretty, I mean, most of the time you would never go this way. Most of the time you would know v and you would take the curl and you would go that way. But you'll see how this is helpful. But I'm allowed to do it because if the two things are equal, then I can integrate the same things and get equality. So let's see. Now I'm in a position to use Stokes theorem, because Stokes theorem, this is exactly the term you see in Stokes. And I'm going to draw that picture. I'll just do it. Okay, here's my jellyfish net. Here is my C on the bottom. Okay, and then we're kind of looking at it from above, like a bird's eye view, sort of. So take a guess. That's my N. Ask yourself, does the orientation of S agree or disagree with the orientation on C as its boundary? So just think in your head. Don't write it in the chat. Just let people think about it on their own. If the boundary of S is plus or minus C. Okay, think about this for a second, and as you think about that, I'll set up this. So this is equal to plus or minus C v dot t ds. So if I'm going to show you the answer. This is like Dora the Explorer. It's like she asks a question, waits 5 minutes, and says, "Yes, the barn is red." Okay. Okay, how am I going to do this? Didn't draw this very well. Here. So here's my normal N. And I'm going to draw some red circles around the base, going counterclockwise. And then I'm going to really just draw more C's. We actually see that we are getting that they're agreeing at that point. So good. So that means positive on all of these things. Okay, and then so positive, positive. And now this is going to be equal to, I'm going to do a quick parameterization in my head. I know you could do all of this because this is just a parameterizing a circle, and I hope that by now everybody could do that. That is the integral from 0 to 2 pi, positive from that positive on the outside. I'm really going to write this. This is negative sine of t over 2, comma, cosine of t over 2, comma, 0, dotted with, I need just another sine of t, cosine of t, 0 dt. And finally, if you do that dot product, you get 1/2 the integral from 0 to 2 pi, sine squared plus cosine squared. I'm just going to skip that and write a 1 dt. And now you can see that's 2 pi over 2, and that's pi. So two totally different ways to show that no matter how creative and squiggly of a surface S you get, you'll be bound to wind up with pi as an answer when V is that vertical vector field. So two different ways to see that. Okay. All right. The next thing I want to do, unless there are questions, which you can stop me, I'll keep my eyes open for that. Okay. I've been sloppy with page numbers. So that was 2, 3, 4, and 5. Okay. So I'm gonna do a question from one of the finals. So this was spring 15 final number 7, and this is kind of interesting. So this was a really satisfying experience. A couple people were in office hours about a month ago, and there was part B of the question that asked to compute something, and I was like, I had no idea how to do it, but it's really only doable once you know Stokes theorem. So I'll walk you through that. But it was enlightening because I had told some of you students, I had said, I have no idea how one would ever do this, even if you had 100 hours. But okay, whatever. It's a really satisfying expression. So let's do. So they give us a curve C of t is equal to e to the sine of t, comma e to the cosine of t, and t ranges between 0 and 2 pi. And you can check that. At first you might think that this would just do some path, but this will give you a closed loop. So this is a closed curve because c of 2 pi, the end, is equal to c of 1, the beginning, where you can compute both of those is it's going to be e to the 0 comma e to the 1, which is 1e. Okay, so the idea is that this curve looks like some wild thing with starting initial point right there. I have no idea what it does. Let's just say it does something like that. Who knows? So that might be C. And then they want us to compute the work integral along C if v equals e to the xy, e to the x plus sine of y. Okay. So the idea is that you look at this parameterized curve, at least my highlighter, and it's garbage. It's a nightmare. You got e to the cosine, e to the sine, e to the trig is really difficult to do, and we can see we'll get those kind of integrals. We'll get those functions inside of an integral, and I have no idea even how to do just like one of those on my own. So the idea is they want you to compute this thing, but likely they want you to use a different approach than actually computing everything by hand, taking the partial vector field, dotting things out, and doing an integral from 0 to 2 pi. So in fact, you should be in your head, think, I can use 2D Stokes theorem. So in order to do this, all you need to do is compute the curl. So the step 1 is compute curl of V. And I'll leave this to you all as something to check on your own. It's really easy to check that if you just compute it out, you get 0. So I won't do the computations in front of you, so I can say on your own if you like, to try on your own. I bet everybody could get it probably on the first try. So you compute the curl of 0, and then you notice that the vector field, there are no singular spots. So we're not dividing by 0, there's no natural log, and there's no even square roots, like square root or fourth root or anything like that. Okay, and so to compute this, we can say that the single integral of v dot t ds is going to equal the double integral over the region R which it bounds. So I'll do that in red. You can even see that the orientation of the inside, the counterclockwise rotation, is agreeing with the orientation of C, or actually, I don't know. I didn't check it. I don't know if, yeah. I'm looking at this curve right here, and I don't know if it moves this way or if it moves the other way, but it doesn't really matter so much. I can write it as plus or minus, but the integral of cosine dA is, sorry, the integral of 0 dA is always 0. So this is going to be plus or minus 0, so that's 0. So I don't know how many points that was, but if you could immediately recognize to use Stokes theorem, this was a pretty quick question, because that curl computation is not that difficult. But the fun question was the part B. So I'm going to move on to this part B. Okay, 5, 6. So this is spring final number 7. Okay. And so B says, consider path C of t equals sine of t plus t, comma, t times t minus 2 pi. Okay, where t ranges between 0 and 2 pi. Now you can actually check that this is not a closed curve, because we can see its initial point and its terminal point. So I'm going to draw it. If my c of 0 is just going to be, it's just 0, 0. So that's c of 0, and then c of 2 pi turns out to be out here. This is 2 pi comma 0, but these don't matter so much. This is c of 2 pi. Okay, and I think it is something like this, but you don't really need to know what the shape precisely looks like. But it is not a closed curve. So that's going to be c, and then so here's the trick. The trick is I'm going to artificially introduce this other curve, c, right here, c twiddle. And so now you see that c2 and c twiddle, sorry, c and c twiddle are now combined, bounding a region R. Okay. Okay. And so, so now if I have any vector field V, I can use 2D Stokes to say that the double integral of the curl of V dA over region R is going to equal, I'll tell you the orientation is disagree on both pieces. So minus C V dot T ds minus C twiddle V dot T ds. So this is what Stokes theorem says for any single vector field. Notice that this question, oh, sorry. I didn't finish out, I didn't write the rest of the question. Okay, I'm sorry. So 7b tells you this curve, and then what they're asking for is compute the area bounded by C and the x-axis. Okay, sorry, I forgot to fill that in. But when I was going through the exam banks a month ago, I saw a question like this, and it said compute the area. So I immediately thought it would be a midterm 2 topic, but it's really difficult to do this question without either computers or Stokes theorem. So here's the cool thing. So we're really looking for the area of this red region R. We're really trying to find the area of that. And we know I'm seeing it appear right here as at least as a region. So is there any vector field that you know that has like constant curl that's non-zero? And you can answer it in the comments if anybody knows off the top of their head. Something that has curl, there's a vector field that you've worked with that has constant curl equals to 2. Yes, good, yeah. So people are suggesting the negative y comma x, which is the rotational vector field. So let's just sub in v equals negative y comma x. So the left-hand side becomes, let's see, okay, the double integral over r 2 times dA. And then the right, I'm literally just going to copy and paste. I've got no reason to, like, okay, I've got no reason to replace the v. Okay, Lily Plaza. Okay. I don't know if Lily, if you're getting me on this angle, which you might be, which is totally fair. Only for the vector fields. So okay, there's the asterisk here that says for all vector fields without singularity in R. Okay, that's the, yeah, that's a good point. Yeah. Okay, so let's see, what am I trying to say here? I'm going to keep this box, this left-hand side is okay, and this thing over here is twice the area of the region R. The area of the region R is what the question is trying to get us to compute. So I'm just going to copy this, move to the next page. I'm not actually going to I'm not actually going to do this. I'm not going to compute the right-hand side, but so this tells us, so thus the area of R is equal to 1/2 this stuff right here. And I believe all of you, well, I mean, I actually haven't done this on my own. I actually haven't run these numbers and seen if these are doable integrals, but I bet they are. And I'm not going to do them here in class because like the harder one is C, but they've actually given you the parameterization. And sometimes that's the most difficult piece. So I think on your own, you can compute this. It shouldn't really be that hard, but the neat thing, I mean, what we were trying to do in office hours were all these crazy techniques of like, we were trying to cut it up into horizontal lines and vertical lines and get y as a function of x, and it was really complicated. And this is a beautiful way to do it if you were somebody who was stuck on it and didn't see that there was like a vector calc way to do it. So sometimes it's like, you know, this stuff is cool because it makes old calculations way easier. Okay, all right. So I'm going to move on. I realize that there is one very, very, very small detail that I said something incorrect to you all like 2 weeks ago. And it's such a fine detail that it really hasn't like shown up anywhere. But there is one question that was on, well, we're going to do it. It's final spring 17 that really requires you to know this definition. So it's the definition of a vector field being conservative. So, okay, and before I move on, y is the negative integral over c and c twiddle. Y is the negative integral of v dot tds over c. Oh, well, because we need, they're both clockwise. You see where we need 2. We definitely need 2 to like fill in the whole boundary. We need to make a closed curve. And then the signs are exactly what Lily said because they're both clockwise. You could do the picture. You could go up to each piece and like draw the thing. Counterclockwise, that fights. Counterclockwise, that fights. Okay. So let me say what I told you incorrectly. So in class 2 weeks ago, I said that curl free means conservative, like as a definition. It's not quite the case. Let me tell you what the real definition. So that goes in a red box. This is false. And the real definition is this: the definition of a conservative vector field V is a vector field such that there exists a potential function f defined on the entire domain of V, and this is i.e. V is the gradient of f. And this works for both 2D and 3D vector fields. Okay, so there's the idea here is that all cats are mammals, but not all mammals are cats. Like this is what I was saying. If you ever teach a 102 class, you say all series. Okay, how do you say it? All convergent series have terms going to 0, but not all series with terms going to 0 are convergent series. This is like somehow this is a richer condition than just being curl free. So the big kicker example, here's an example, is that V equals the one we've spent so much time on. It looks like rotation, but it's divided by an r so that you can have 0 curl. So x squared plus y squared. Okay, so what am I trying to say here? Example, this thing. Okay, so this vector field is curl free, but is not conservative. And let me is curl free. What do I want to say? Where defined this vector? Oh, easy to compute. This is easy to compute, but it is not conservative. The reason why it's not conservative is because you can find closed contours, you can find closed loops in the domain of F, in the domain of V, which have non-zero work integrals. So let me, like, maybe people have a whole bunch of questions, but there's a really good question on final spring 17 that sort of might answer a whole bunch of questions you might have at this point. So let me just jump right into final spring 17. This is number 2A. Okay, do I have enough time? Yeah, okay, good. Okay. Okay, so A is saying, A just says give definition of what it means for a vector field to be conservative. So that's basically easy points. If you just know if you know the definition, you can just say it. It's there is a potential. There's a single potential function. A single potential function. Okay, for V. Okay, that was A. 2B is that literally I'm just copying what was the definition I gave you over here. It's just, do you remember the definition? So 2B says is true or false, saying if V is P over Q, so sorry, P comma Q, so we got a 2D vector field. This is defined everywhere. So no discontinuities, no nothing. Okay, go away, and then except the origin, sorry, except the origin. So you might be having this over here in mind. So that's defined everywhere except the origin. And then it says, okay, what's it? Defined everywhere except the origin, and V is conservative. Okay, so these are axioms, and it says then curl of V equals 0. So they want to ask, is it true, knowing the data up here, is it true that the curl of V has to be 0? And the answer is yes, it is true, because any vector field that has a parent function, when you compute its curl, like the mixed partials subtract from each other and you get 0, because like partial squared xy is partial squared yx. Okay. Okay, so the answer is true. Let me circle that. The answer is true. All right. Okay, and then they asked the other way around. So what they were saying here, this business with the except, okay, this whole defined everywhere except the origin, that really was not necessary to do the problem. They're just kind of throwing extra stuff in there to throw people off. But if you really know your stuff, then you'll know this is because conservative always implies curl 0. So it doesn't matter the domain, doesn't matter nothing, just conservative is the stronger condition. This is the richer condition. Now they're going to ask the opposite way, and it's going to be false. So number 2B, true, false, is it the same? I could just copy and paste that. I'll write it all out. So V is PQ defined everywhere except at a point. Okay, and then you say, so another a clause or a given is, and suppose you know curl of V equals 0. So then V is conservative. You say no, so this is false, because, and a counterexample is, I'm just going to go to the previous page and copy and paste it. This thing right here. It's going to take that whole thing with me. Yes. Paste. Okay. Awesome. So that's a counterexample. Then there was a D and an E, but I have 9 minutes. I think I can do it. Let's do D and E for the same question. So now we have final. Spring 17, number 2, D, and it says true or false. If V is a conservative vector field, then the divergence of V is equal to 0. So at first, when I was doing this problem last night on my own, I sat down and I thought, oh, this probably seems right. This will probably happen. And I actually computed it. So when I was doing this myself, which is how I would hope people would probably do a problem similarly in an exam setting, you would say, well, V is conservative tells me that V has to look like this. It has to have a parent. So now, instead of taking the divergence of the left-hand side, I can just take the divergence of the right-hand side. And this is going to be partial squared f partial x squared plus partial squared f partial y squared. And I have no reason to believe that this thing is always going to be 0. And in fact, it's not always 0. If I pick f is x squared plus y squared, then I know the gradient of f is, I'll put a half out here actually, is x comma y, and then I can take the divergence of the gradient of f, and this is equal to 1 plus 1, which is 2, not 0. So I'll highlight the answer. The answer is not true. The divergence does not need to be 0. It could be 2 or something else. I'm just going to minimize so I can save on the same page. Oops. It would be so cool if I could get to the last example. Okay. See, D and then E. Okay. So this is same. This is number 2E is asking true false. If V is conservative, then the curl of V equals 0. And then this is like a freebie. This is like yes, true, because this is where you get the mixed partials commuting. Mixed partials commuting in your curl computation. In the Venn diagram looks like this. The Venn diagram is like conservative, and then out here is curl free. And there are points that are, there are vector field, there's stuff here that's not in here, and that's something like the one we were talking about, the rotation-y thing. Okay, so that was 17. I knew I had to go over this with everybody because it was like the mistake I made was just too sad to have given you an incorrect statement and have you walk into a final with having bad information. So I knew I at least owed it to at least go through this whole problem. But there's one last question example that I want to do in this class. And it's pretty cool, and I think we can do it in 5 minutes. So here's the last example that we'll do. So claim let V of x, y, z be any vector field in 3 space. You can say no singularities, so it's defined everywhere. I don't really care about that so much right now. So I haven't made the statement. The claim is going to be then the double integral over the sphere centered at the origin. So sphere unit centered at origin. I'm not going to take the flux of V through the surface n. I'm going to take the curl of V, flux it through the surface n, and then dA it. Then this equals 0 all the time. So two ways to prove this. Oh, I should tell you what the n is, because is n going to be the in or the out? That matters. At least it shouldn't if we know it's 0, but whatever. I'm going to tell you n is the outward. Okay. Okay, so we've got this piece. I'm going to proof 1. I'm going to use the divergence theorem. So this is the divergence theorem. It says that, so I'm going to do an intermediate step, and I'm going to write the above. I'm going to call curl of V, I'm just going to call that W for a second. So above, we have the double integral over S, the curl of V dot N dA is just going to equal the same thing with the W, literally just because I've named it differently. That might sound silly right now, but it'll help. I think it helps because I want you to see the step that is the divergence theorem, and it would be messy if there were curls flying around. So now the divergence theorem says that the integral of the flux through the edge is going to be the divergence on the inside. So this is equal to the triple integral over the omega, which is the inside, of the divergence of W dV. And now I'm punting this to the homework. In your homework, I ask you to compute that the divergence of the curl of any vector field V is always equal to 0. This is like kind of analogous to the fact that the curl of the gradient of F is equal to 0. There are lots of these similar like computations that float around. Okay, and so I can say that this is equal to changing back my W into what W really is. I'll highlight it. Really, whenever I see a V, I really just artificially named it V, but really that's the divergence of the curl of V dV, and now this thing is always 0 by homework. You've already proved that, or you will very soon. And so thus the whole thing is 0. Okay, so that was proof number 1 using divergence, and I bet we can do the second one using we're going to use Stokes theorem, which is its alternate proof to do it. Okay, so this is proof number 2, Stokes. So we're going to be doing singly line integrals instead of triply integrals. I'm going to just copy and paste the whole thing so we can just see it. But we can do this. I'm sure we can do this very quickly. I bet we can do this. Yeah, not even having to do overtime. So I'm going to divide divide sphere into upper hemisphere, upper hem, and lower hem. So I'm going to call that H1 and H2. Okay, H1 is going to be the upper H2. So that S is H1 plus H2. And so that the double integral, I'm going to drop all the middle stuff. The double integral over S is going to equal the double integral over H1 plus the double integral over H2. But now I want to use Stokes to compare these things with the single integral around the boundary. So the boundary of H1, I'll draw it up here. C is this counterclockwise. I'm going to orient the equator counterclockwise, and this is an outward normal. So there I have agreeing on H1. So here I have boundary of H1 equals C, and you can check that the boundary of H2 is negative C. So what you have is, I didn't finish. Okay, I can finish it now. That by Stokes, applying Stokes twice, this is the single integral over C v dot t ds minus, and we're both, it's like C on both bottoms because it's the same boundary that's shared, minus the single integral of the work along the bottom edge, which is the same edge, and that cancels to be 0. Okay, so those are two different ways to see the same result. So that's, yeah, so I'll have my office hours, and you can say after class, I'll stop sharing.